Okay, practice exam 2. So continuing on from before, let's begin. The first question asks us to find the derivative dy dx. So the first one, y equals x tangent y. We've got to use implicit differentiation. So differentiate the left-hand side, that's just dy dx. Here we need to product rule, so first d second derivative tangent is secant squared, but we need to tack on a dy dx. So we differentiated a y, which is a function of x, and then plus second d first, derivative of x is just 1. Okay, move all the terms with dy dx on one side. That's what I did. Factor dy dx and divide to solve for dy dx. That's what I did there. 2 steps in 1. Okay, so number 1, A, B. This is the easiest problem probably. Fundamental theorem of calculus. I always say this whenever it's fundamental theorem of calculus. This type of the problem, easy points. How do we do this? Plug in the upper bound times derivative of the upper bound minus plug in the lower bound times derivative of the lower bound. If we differentiate the upper bound, it's 0, so there's no first term. So we start from the second term. Minus plug in the lower bound times derivative of the lower bound. So if we simplify, derivative of cosine is minus sine, but there's already a minus there, so we can write it as sine x squared of 1 minus cosine squared x. Okay, and I would just leave it like this, because technically, it's a 1 minus cosine squared sine squared, but then you have to worry about the domain and all that, so just leave it like this. And this is what the professor did, honestly. So this is sufficient for at least this professor. Again, if you want to simplify 1 minus cosine squared to be sine squared, you got to be careful when you take the square root because of domain and everything. Okay, let's continue. Given that f double prime is this, f of 1 is this, f prime of 1 is this, find f of x. This is the antiderivative problem. Okay, the clue should have been we're going from f double prime to f. That's the first clue. You got to find the antiderivative. And then they give us 2 initial conditions as well. And that's required if you're going from the second derivative to the first derivative. You have to have a condition for the first derivative and a condition for the the 0th derivative, which is the original. Take no derivatives. Okay, so we start from the second derivative, we find the antiderivative, or we integrate f double prime, which is this, to get f prime. Okay, we just use the power rule. So first of all, I just divided through by the x cubed, so I wrote it as a negative exponent here, and this would just be 1 power of x, okay? We use the power rule, and don't forget your plus c. We can find the c because they gave us the initial condition that f prime of 1 is 3. So we can plug in x is 1 into here and solve for c. c would be 3 plus half minus 3 halves, which is 3 minus 2 over 2, which is 3 minus 1, which is 2. Okay, so this is the general solution. Our particular solution, because they gave us the initial condition, is this over here with the c that we found, c equals 2. Okay, now we go from f prime to f, we integrate again, or anti-differentiate. Okay, so again, we just use the power rule, and don't forget your plus c. There's a different c than this one, by the way, so you can use a different letter if you want. That just should be fine. Okay, and then they gave us the initial condition f of 1 is 1, so we're going to use that. So plug in x as 1 into here, and then solve for c. c is 1 minus half, minus another half, minus 2, which is minus 2, negative 2. Therefore, our particular solution and final answer of f of x is half x to the minus 1 plus half x cubed plus 2x minus 2 from this here, and no more plus c because that was our c. Okay, so this is a typical problem of anti-differentiation, finding antiderivative. And this is the most basic case of differential equations. Okay, moving on. Find the absolute max min of this guy on this interval. Okay, so we probably want to differentiate to find out if there's any relative max min inside this interval. And then we check the endpoints, because we have to when it's absolute max min. Okay, so let's differentiate this. We need the product rule, first d second plus second d first. So first d second derivative of square root is 1 over 2 root x, but it's a composite function. So we need a chain rule. So derivative of 1 minus 4x is negative 4. Okay, plus second d first. Derivative of x is just 1. Okay? Factor out the 1 minus 4x to the minus half power, which is 1 over square of 1 minus 4x. So I factor that out. By the way, minus 4 divided by 2, that's minus 2. There's still an x there. Okay, and then I factored this square root on the bottom out. Plus, if I factor out this from here, it's half minus negative half power, which is first power. So that's 1 minus 4x there. Okay? And then we simplify. This is minus 6x, right? So right there. Okay, so the critical points are when x is half, x is 1/6, that makes the top 0, and when x is 1/4, that makes the bottom 0. Remember, critical points are when f prime is 0 and when it's undefined, okay? So 2 critical points. So we don't need to do all the interval decrease, increase, decrease, that stuff. We don't really care because we're interested in absolute max min. So we can just directly evaluate the function f at negative 1/4, 1/4, and 1/6. Okay, this is a duplicate, right? So at those 3 points. That's what I did here. If we go through the math, f of minus 1/4 would give you minus 1/4, which is negative. Okay, so let's keep in mind that's negative. F of 1/6, we plug in x equals a 6 into here. You would get this number, which is hard to simplify, but we know it's positive. Okay? And f of 1/4 is, when we plug in x as 1/4, we get 0. Okay? So, when you plug them in, if you didn't realize these, one is negative, one's positive yet, this one's easy to tell that's 0, right? Because it's 1 minus 1, which is 0. Okay? We're interested in absolute max min. So if this is 0, this one's clearly negative. Well, this one's easy because it's minus 1/4, that's negative. But this one, clearly it's positive. Okay, so we only care, because there's 3 values and one of them is 0, we only care which one's the biggest and which one's the smallest. That's the absolute max min, right? Negative is clearly the smallest of the 3. So that's the absolute min. F of minus 1/4 is whatever that is. So you should write it as the actual points, not like how I did it over here, but besides the point. And the max is the biggest value. The positive is clearly the biggest. One's negative, one's positive, clearly the smallest and the biggest respectively. If this one's 0, right? So you don't really have to know this value actually. But like in decimal form to kind of compare. You just need to know if it's positive or negative, basically. And kind of repeating myself many times, but hopefully you get the point. Okay, so that's how I approach this one. Okay, evaluate the definite integrals. So the key point for absolute value integrals with absolute values is you got to find out if the function's ever negative. Okay, and it is when square of x minus 1 is negative on the interval 0 to 1. Okay. So, because we know that, we need to flip the function, the sign of the function, before integrating that interval. Because remember, if the function is negative, it's below the x-axis, which means negative area. But we want the absolute value. So we got to flip it to make it positive, okay? So, because we found out that it's negative between 0 and 1, that's within this limit of integration. So from 0 to 1, we take the negative of the function, 1 minus square root x. And then from 1 to 4 onward, it's always positive, so we just take it as is. Okay? Then we do the power rule and fundamental theory in calculus. If you simplify, you should get 2. So you can check your math against this if this steps up, but the final answer should be 2. The key point, again, was you got to flip this portion over here because it was negative. And we're wanting the absolute value, so you got to make it positive. Okay, then this integral, hopefully you can see that is a very obvious substitution. Let u be 3 minus x squared. Du is minus 2x dx. By the way, I said is hopefully you recognize it's a very obvious substitution. So hopefully if you don't see that right away, do more practice problems on substitution. These should be a no-brainer, especially when you move on to the next course. These simple substitutions like this should be no-brainer. Okay, so to get to that level of competency, do a lot of problems. Okay, so let's substitute. It becomes this x dx is du over minus 2 or minus half du. Okay, and this is square root of u. Okay, now it's a definite integral, so don't forget your limits of integration. So I always substitute and then do limits of integration. That's just my habit that I do, and I don't think I ever forgotten actually, because I had this habit ingrained in me from the beginning. But you have to keep that in mind. Whenever it's a definite integral, you have to change the limits of integration. Or technically, you could back substitute the original variable and keep the original limits. You can do that, but usually substituting the limits make the math easier. Okay, so when x is 0, u is 3 minus 8, which is 3. When x is 1, u is 3 minus 1, which is 2. Okay, you can technically evaluate this integral from here, but you probably think it doesn't look nice because it's from a big number to a smaller number, bigger number to a smaller number. We can flip the limits and add a negative sign. So that actually would make things nicer because there's already a negative sign here. We make it positive then. Okay, now we just use the power rule, fundamental theorem of calculus. That's your answer over there. You can check there. Okay, so it's number 4. I feel like I'm moving a little faster in this exam. Okay, calculate the limits. Do not use L'Hopital's rule. Okay, this is actually the same question as in the first practice exam. Now it's just an x instead of t. The trick was you use a special trig limit. So here's the answer. It's 0. You have to use a special trig limits here. Okay. So the same question as before. This one is a typical horizontal asymptote question. Limit as x approaches negative infinity of square root of 9x to 6 minus x over x cubed plus 1. The trick here is you want things as like 1 over x to some power, because when you take the limit as x approaches infinity or negative infinity, it goes to 0. So the technique is you want to factor out the biggest degree. The biggest degree on the bottom is x cubed, so we're going to factor that. Inside the radical, the biggest degree is x to the 6, so we're going to factor that inside the radical. So that's what I did here. Okay? Now, we can use properties of radicals to split this up as square root of x to the 6 times square root of 9 minus 1 over x to the 5th. When we take square root of x to the 6, technically it's plus or minus x cubed, right? But x is approaching negative infinity, so we're going to take the minus. So another way to write it is square root of x to the 6 is opposite value of x cubed because it is plus or minus x cubed, right? But we're approaching negative infinity, so we take the negative. Okay? That's one way to think about it. You got to be careful sometimes, but in this case, because as x cubed approaches minus infinity, it's minus. Okay? I'll talk about a different way in a bit, which the professor did, which actually can be nice in some cases. But anyway, these x cubes cancel. So you're left with here. Now you take the limit as x approaches negative infinity. This term goes to 0. This term as well goes to 0. So that's what I was saying. We want it as 1 over x to some power. That's a positive power, by the way. So that it goes to 0 as x approaches infinity or negative infinity. Okay, so you have minus 3 as your answer. So what the professor did was he, you could rewrite this as, let's let y equal negative x. Do a little substitution. So limit, instead of x approaches negative infinity, if you want it in terms of y, if x approaches negative infinity, what does y approach? You can kind of plug in negative infinity as x. The y approaches positive infinity, so I'm just going to write infinity, okay? And then wherever there's a x, you plug in minus y, okay? So it would be square root of 9 minus y to the 6 minus negative y over minus y cubed plus 1. Okay? And if you go through the motions, you should get the same answer. So I'll let you try that, but this is one other kind of like hack you can do. Okay, so that you approach infinity instead. Okay, instead of negative infinity. but you should get the same answer. So this way or this way, up to you. Okay, I'm not going to go through it here in the interest of time. Calculate the area of the region of the plane bounded by the curves y equals x squared, y equals 2 root x. So for these, it's always good to sketch out the region quickly. You should know how these look at these points. Just quickly sketch it. Square root of x looks something like this. 2 square root of x looks something like that as well. Okay, this is just a rough sketch. X squared is a parabola, looks something like this, right? So area is upper curve minus lower curve. So it would just be 2 root x minus x squared dx. But what about our limits of integration? How do I get that? Well, we need the points of intersection to determine our start and stopping point. This one's clearly easy to tell as when x is 0. Okay, what about this point over here? It's a point of intersection, so we can set x squared equal to 2 root x and solve for x from here. Okay, so a square both sides, x to the fourth is 4x. Move this 4x to the other side, factor. So clearly x is 0 is one of the solutions. That's what we knew right away. And the other one is cube root of 4. That's this one over here. X equals cube root of 4. That's our other limit. Okay, now we go through the motions to evaluate. We need the power rule and then plug in the limits. So the final answer should be 4/3. Okay, by the way, when you plug in cube root of 4 into like here, cube root is 1/3 power. So 1/3 power, so 1/3 times 3/2 would become half. Right? So it'll be 4 to the half power, which is 2. Okay, so that's, if you didn't get that part, that's there. Okay, so area between curves, again, it's helpful to sketch the region. If it's in terms of x, then upper curve minus lower curve. Okay. This is a related rates problem. Blimp flying parallel to the ground at a speed of 24 mph releases a weather balloon that rises vertically at a rate of 6 miles per hour. How fast is the distance between the blimp and the weather balloon increasing 5 minutes after the release? Draw a diagram first, as always. It should help you visualize what's going on. I didn't do it because I was typing it, but let me do it now. Okay, so flying parallel to the ground at speed of 24 miles per hour. So let's say the blimp is going this way, right? And the weather balloon rises vertically at a rate of 6 miles per hour. So it's going like this way, right? It's a triangle. This is the distance. Let's call it A. Okay? Call this X, call this Y. I don't want to call it D, distance, because we're going to differentiate. So I don't want to confuse you. So I'm calling it A, okay? Okay, so for related rates problems, I always write out in variables what they give us. This is the rates, 24 miles per hour. So they gave us dx dt, actually, 24. 6 miles per hour, again, is a rate. They gave us dy dt. Okay? You got to be careful. 5 minutes, these are in hours, by the way, miles per hour. So you got to convert this to hours. 5 minutes is 1/12 of an hour. Okay? And they're asking for how fast is the distance between the blimp and the weather balloon increasing. They're asking for this rate of change of A. They want dA dt. So we got to find a formula that relates these three. We know one is the Pythagorean theorem. A squared is x squared plus y squared. We want dA dt, so let's differentiate. 2a dA dt equals 2x dx dt plus 2y dy dt. You got to pleasantly differentiate. All right? So do we have everything to solve for dA dt? Not quite. We have dx dt, dy dt. Do we have x, y, and a? Well, 5 minutes after the release, how much is x? 24 miles per hour. 5 minutes after, or 1/12 hour after, that is 2. So it went 2 miles. The weather balloon, 6 miles per hour times 1/12 of an hour, that's half a mile. Okay? So we can use Pythagorean theorem. A would be square root of 2 squared plus half squared, okay, which is, if I simplify, square root of 17/2. Okay, now let's plug everything in. We have everything now. And don't forget units. Actually, the professor forgot to put units in his answer, his or her answer. So I would mark that wrong, actually. So don't forget your units. So dAdt is all this shenanigans over here. If you simplify, you should get 102 over root 17 mass per hour. Again, don't forget units. I would take points off if you don't have this. Okay. Function defined by this, probably fundamental theorem calculus will be needed. This is a variable as a limit of integration. Find the intervals on which f is concave up and down. Okay. So we need a second derivative. That second derivative is related to concavity, right? So let's differentiate this guy twice. If we differentiate it once, fundamental theorem calculus, we plug in the upper bound, times derivative of the upper bound, which is just 1, minus plug in the lower bound, times derivative of the lower bound, derivative of 0 is just 0. Okay, so f prime is we just plug in the upper bound as the variable of integration. Okay, second derivative, we need the quotient rule. Or you can use product rule, up to you. I use the quotient rule because usually a little hint that sometimes it's easier to use the product rule, but then the algebra to simplify sometimes gets a little complicated. So it might be just worth it to use the quotient rule from the beginning, even though it's more difficult to use the quotient rule per se, but you don't have to do as much weird algebra to simplify. Okay, so I just directly use the quotient rule. So bottom, d top, derivative of top is just 0, minus top, derivative of bottom, that's 6x plus 6x squared, over bottom squared. Okay, the top I can factor out as 6x. Right, so the critical points are 0 and negative 1. Okay, the bottom is never 0, so we're good there. Okay, do the first derivative. Second derivative test, sorry. So we put our two critical points. We plug in a huge negative number. The bottom's always positive because it's always squared, so we don't care about that. Let's just keep focused on the top. Huge negative number. There's a negative here, another negative from that huge negative number, and another negative from that huge negative number. Okay, 3 negatives make a negative. Plug in something between minus 1 and 0, like minus half. This would be negative from here. This would be negative as well. This would be positive. So 2 negatives make a positive. Plug in a huge positive number. This would be positive. This would be positive. But there's a negative here, so negative. So it's concave down between minus infinity to negative 1, union 0 to infinity, and concave up between minus 1 and 0, not including the boundaries. Okay. That's number 8. Okay, the volume questions, remember I said, always draw out the R out, R in, or the R and the H, depending on the washer or shell method. So they give us that now this time the curves are the regions bounded by the first quadrant, y equals 2 minus x squared, y equals x, and the y-axis, okay? So let's sketch the region first, as always. 2 minus x squared is this parabola. It's shifted up by 2, but it's opening downward. Y equals x is a linear line. That should be easy. This is the region. It's bounded by the y-axis as well. Okay? We're going to revolve it about the x-axis. So this is the axis of rotation. So if we want to integrate in terms of, or if we want to do washer method, it's easy to integrate in terms of x for horizontal axis of rotation. Okay? Which we're set up for that. These are functions of x already. So we can draw an r out and an r in. So start from the axis of rotation, draw it to the further function. Start from the axis of rotation, draw it to the closer function. That's your r and r in respectively, okay? So our r out, what's the length of this r out? That's just 2 minus x squared. R in, what's the length of this? That's just x. So x, and then we square it from there, okay? Limits of integration, well, clearly it starts from 0. What about this point? We need to find a point of intersection, so set these two curves equal to each other. And you find that x is equal to what? Okay? Now this one asks us to revolve it about the y-axis. So if it's a vertical axis and our functions are in terms of x, it's nicer to use the shell method. So we need to draw a height of each shell. So notice that for the shell method, the the shell cross-section is parallel to the axis of rotation. And then from the shell, we draw a radius r to the axis of rotation. Okay, so what's this length r? That is just x. What's this length h? That's 2 minus x squared minus x. So across whatever I wrote there, so 2 minus x squared minus x, as I just said. Okay, limits of integration, same limits, because we're integrating in terms of x. So from 0 to 1 again. Okay, I think I'm moving faster in this exam, unless this problem will take long. Okay, function f has the properties f of 0 is 5, f prime of x is less than or equal to minus 3 for all x in 0 to 2. Prove that there's at least one solution to the equation f of x is equal to 0. Hint, what can you say about f of 2? Okay, so how can we use that hint to our advantage? And this should sound familiar. Prove that there is at least one solution. So we probably want to use which theorem? The intermediate value theorem. So how can we use the intermediate value theorem here? Well, there's a condition to use the intermediate value theorem, first of all, which is that the function has to be continuous on that interval. Okay? Is it continuous? It tells us that it's differentiable because f prime has some value between 0 and 2. Remember, if something's differentiable, it's automatically continuous. Continuity is a prerequisite for differentiability. Remember, something's not differentiable when it's not continuous. That was like 1 to 3 cases for when something's not differentiable. Okay, so one of the conditions is met. Okay, now we got to find one point that's negative and one point that's positive. That's positive. Such that, since it's continuous, and 1 point's negative, 1 point's positive, it has to cross 0. That's the whole idea of intermediate value theorem. Again, I said this in the other video. I have a short on this to recap that concept if you don't quite remember it. So you can go watch that if you want. So we got to find a point that's positive and a point that's negative. Okay, so we already have a positive point. F of 0 equals 5. We need a negative point now to show that it crosses the x-axis, or it crosses y equals 0. How can we get a negative point? Well, this is the key. F prime is less than or equal to negative 3. Okay? So since f prime is negative, that means f is decreasing on this interval, which means that f of 2 is less than f of 0. That's good to know, first of all. Okay? Again, because f prime is negative, the function is decreasing. Since it's decreasing on this interval, then the value at 2 must be less than the value at 0. Okay? Now, let's assume that f prime is exactly minus 3 on the whole interval. Okay? This is the smallest rate of decrease, by the way, if f prime is minus 3. Okay? So it could decrease even more, but I'm taking like the worst case, kind of, when it's the least. Okay? Imagine if it is a constant negative 3. Then it's a linear line, so we could easily find the value of f of 2. It's 5, take the rate of change, minus, this is like the slope, minus 3 times 2 minus 0, that's the length. So this would be negative 1 when you evaluate it. So since this is the smallest rate of decrease, that means f of 2 is less than or equal to negative 1. It could be even more negative if this is more negative. We don't know, but this is the worst case. We found a negative value right here, did we not? This one's negative. This one's for sure negative. Okay, so now we can put all the pieces together to use the IVT, intermediate value theorem. Okay, so that's what I did here. Since f is continuous on 0 to 2, f of 0 is greater than 0, given. I don't know if I pointed it correctly, so the timer's blocking and when I'm filming. And f of 2 is negative. Then by the intermediate value theorem, there exists at least one solution to f of x is equal to 0 on the interval 0 to 2, on the closed interval. Okay? That's how I thought to solve this problem.